I'm going to focus on electric power in this lesson. So electric power is a measure of the amount of work that can be done by a current in a given unit of time. And we know that the amount of work done to take a charge across a potential difference V is calculated as W work is equal to Q times V. But we also know that the current is equal to the charge over T. Or in other words, we can find Q, the charge, if we had the current multiplied by T. So if we were to combine those equations with work and Q equals I times T, I can replace Q with I times T times V, where W is the work being done, I is the current, T is your time, and V is the potential difference. And power is simply work done per unit of time. So for our formula, we're going to use power is work over time. But we can exchange that W for work as the one that we just figured it out before, which is the current times time times potential difference. And you can see that I can cancel out the T from top and bottom, and then we're just left with I times V. Your units here is going to be in watts or joules per second. So I'm just going to recap what our formula is. I'm going to highlight this because this is the one we're going to use the most to find power. So let's try this in example. How much current is drawn by a 350 watt electric drill connected to a 110 volt power source? So we want to know the current when we're given the power. So I'm going to use the formula that we just derived. I'm going to rearrange because I need to solve for the current. So I is equal to P over V. So the power is 350 watts, and your potential difference is 110 volts. So then we get 32 after we divide 350 divided by 110, and we're looking for the current, which is in amps. We're going to derive a few more formulas that we're going to use. So using P equals current times potential difference. And we also know that the current is equal to V over R. And if I rearrange this to solve for potential difference, it's our current times R, which is the resistance. So we can also calculate power as V over R times V by replacing our current I with V over R, which is then V squared over R. So this is one formula that we could also use. So power is equal to the potential difference squared over resistance. And also we can derive that power is equal to the current squared times R by using V equals I times R. This is another formula we could use. So if you forget what all these variables mean, I can just write them on the side. P is for power. I is for current. V is for potential difference. R is for resistance. So again, we're going to try these on examples. What is the resistance of a 100-watt light bulb operating in a 110-volt field? So here we're looking for R. I'm going to rearrange P equals V squared over R. Because we have P, the power, and we also have V, the potential difference. So our potential difference is 110 volts, and our power is 100 watts. So 110 squared divided by 100 is 121. Remember, our resistance unit is ohms. What is the resistance of a 60-watt light bulb operating in a 110-volt field? I'm going to use the same formula. In this case, our power is different because we have 60-watt light bulb. This would be 201 ohms. Let's do another example. A 115-volt motor that is 75% efficient draws 8 amps when running. What is its power consumption and its power output? So I'm just going to underline some of the key information that we need. 115 volts, 75% efficient, 8 amps. We're looking for the power consumption and its power output. Also, if the motor runs for 30 minutes, we want to find kilowatt hours of power and also joules. The first thing we can do is find the power of the total, which is calculated as I times V from our last page. So our current is 8 amps. Our voltage is 115 for the potential difference. So that means the power in total is 920 watts. So that's one thing we found so far. The other thing we can do is find the power output. And as the output is going to be 75% efficient. In other words, it'd be 0.75 multiplied by the total power. So again, the explanation is 75% of total power will give us the output. So 75% of 920 watts is 690 watts. The next thing we want to find is the kilowatt hours of power for 30 minutes. So looking for the total power used in 30 minutes. So to find the total power used for 30 minutes, we know the amount used for an hour. That's 920 watts for the hour. But because we're looking for 30 minutes, which is equivalent to half an hour, then I can just multiply this by 0.5 of an hour and would get 460 watts times hour. But we also want this in kilowatts. So I had to do that conversion and divide this by 1,000 to get it into kilowatts. So if I divide this by 1,000, we're going to get 0.46 kilowatts times hours. Our last one, we want to find this in joules now. So we know that 1 watt is equal to 1 joule per second. So to find the total power in joules, we're going to take our total power, which is 920 watts. And if we look at a conversion, we need this to be just joules. So in order to get this into just joules, I need the seconds, the time, to cancel out. So I'm going to multiply this by 30 minutes because that is our total time frame of how long the motor is going to run. And I'm going to do the conversion between minutes to seconds. So there are 60 seconds per minute. And the reason why I do that is so I can cancel out our minutes. I could also cancel out the seconds because the watts can be replaced with joules per second, as the conversion I just showed you above here. So our seconds can also cancel out. Then our unit left over is just going to be joules. So we're going to do 920 times 30 times 60, which is 1.7 times 10 to the power of 6, and our units left over is in joules.